Hello, everyone. Welcome. This is SETI Live. I am your host, Beth Johnson. And joining me today, I have Doctors Cherry Ng, who is the project scientist for our new program, Cosmic, which we'll get to, and Dr. Savin Shynu Varghese, who is the postdoctoral research fellow, on the project. Cosmic is the Commensal open source multimode interferometer cluster search for extraterrestrial intelligence. That is quite a mouthful, which is why we refer to it as Cosmic SETI. Yay for acronyms. And recently we announced that we have taken a huge step forward on using the Very Large Array for 24/7 SETI observations. So Cherry and Savin are here today to us about this new project and what it means for the search for extraterrestrial intelligence. So thank you, Cherry and Savin, for being here and joining me. Welcome, welcome. And go ahead, say hi, guys. Say hi.
Hi, everyone. Thanks for the introduction, Beth.
Hello.
And just to do our usual kind of thing here, welcome everybody who's watching. Please let us know where you are watching from, and we will give you some shout outs. And as a quick early reminder, the SETI Institute is a 501c3 nonprofit. So your Twitch bits, your Twitch subs, your YouTube super chats, your Facebook stars, all of those things go to our SETI Talks program and help support outreach like this. And now I want to talk about Cosmic. So Savin, tell us about Cosmic. What is it? Give us a brief overview of what Cosmic is and how it's improving our SETI work.
Hey, I'm hearing like multiple.
Make sure you don't have a window open with the YouTube in it somewhere.
No, I don't have a YouTube.
I hear you fine, Beth.
Okay.
And I hear you fine too, Savin. Maybe you can just
Yeah, now I can hear. Sorry.
Okay.
There's some mix up, sorry. Yeah. Hello?
Yes, are you there?
Yes.
Okay. So Savin, can you give us a kind of brief overview of Cosmic and how it's improving SETI?
Yeah, sure. So Cosmic stands for Commensal open source multimode interferometer cluster. I'm not going into details of that, but this is a collaborative project between the SETI Institute and the National Radio Astronomy Observatory for starting a new observation capability with the Very Large Array radio telescope in New Mexico, so that we can use that system to search for technosignatures or any kind of signals which are not from natural phenomena or from any human-made digital technology. And so with this project, the main idea is that whenever the VLA or the Very Large Array is operating, we'll be able to piggyback on that telescope observations and make an independent digital copy of the telescope to conduct SETI observations throughout. Yeah.
And Cherry, I understand. So we did a press release recently saying that we have installed some of these fiber optic amplifiers and splitters. How many are they all installed? What's left to do? What are these? How are these working?
Yeah, it was a big milestone for Cosmic. As of December last year, we have installed amplifiers on all the antennas on the VLA. So that is the first step to having the capability to conduct SETI research 24/7. Now, as we speak, in fact, next week we are going to install the cable that will connect all the antennas to Cosmic fiber interface. And then what's left to do is that we'll have to install a custom compute cluster to process the huge amount of data real time And then that's it. We'll be live on sky looking for ETI signal 24/7 with one of the most sensitive telescope in the Northern Hemisphere. So I think this is a really exciting project because we have never had that high sensitivity and that amount of on sky time.
So Savin, you have, can you show people what we're talking about when we're talking about the VLA and maybe even what we're talking about with the amplifiers?
Yeah, sure. So most of you might have seen this picture of the Very Large Array. It's located at the central New Mexico on the plains of San Agustin Mountains. You can see the mountains here. It's a it has a Y-shaped configurations. Each arm has 9 antennas. So we can spread these antennas to get a better resolution or to better see the details out in the space. So currently, the data from all these antennas goes to a supercomputer called Correlator, but we are splitting out the signals so that one set of copy goes to our cosmic system. And these are some of the amplifiers and splitters which were installed by the NRAO team, the VLA staff. So this actually enables us to get a complete copy of the data to our system. So once the data is collected from these antennas and splitters, it goes to our signal processing system, which have which contains these 2 big racks and different machines inside this. And each of this machine has something called, if you look at the inside of this machine, it might look like this. And there are some small, boxes kind of stuff known as FPGAs. We can, in simpler terms, we can think of it as like a chips, which can be programmed to do some specific purpose. So in this case, we collect the data, convert them into a particular data format, and we use that for further processing, and especially for SETI searches and stuff.
Thank you for that overview. I love that picture of the VLA. It's so neat to see. Really quickly, I want to give some shout outs. Thank you to everybody who's joined us and is watching from London, Philadelphia, here in Silicon Valley, Illinois, Ireland, the UK, Arizona, Pakistan, Atlanta, Georgia, and a big thank you to both Paula and Douglas for the Facebook stars. Much appreciated. Thank you so much. I do have one question from the audience already that I wanted to ask, so I'm going to go ahead and do that. Is the Y shape on the antenna, is that significant in any way?
Yeah, it is significant. It's significant in terms of like how you can make the image of the sky. And also, so in the case of VLA, you can actually spread the antennas along those arms, basically increase the distance between the antennas. Mm-hmm. So that is crucial in figuring out the details of the image, or it's called something called angular resolution. Basically, you can separate 2 different sources very clearly when you have a better antenna spacing in the array. So
how much room does the VLA have to spread out exactly? Do you know?
Yeah, so there are like basically 4 configurations for VLA. The first one is the A configuration. In the A configuration, the maximum distance between the antennas are like 35 kilometers. And then there is B, C, and D configuration. And in the D configurations, the array is compact. So what I showed earlier is the picture of the D configurations where all the antennas are compact and close together.
Okay, thank you.
Yeah, basically when the antennas are the furthest apart, then they have a really long baseline, and we can triangulate to very fine spatial resolution, and we can see a very detailed images. But when the antennas are closer apart, on the other hand, we'll be able to look at a larger area of the sky at the same time. So it depends on what your science goal is. And the VLA is special in the sense that it has this flexibility of moving these antennas around to fit the purpose of the astronomy project.
So one of the things that comes up a lot when I'm writing or talking about SETI and how we're listening for signals is this idea that somehow radio is passé. It's old technology. Cherry, can you explain why that is not true and why we're continuing to use radio observations?
Right, yeah, I think radio is still a prime target to look for ETI signal. Just look at our own civilization. We are heavily using radio transmission to for communication purpose. So it's by no means an outdated technology. Radio is also relatively cheap to produce and can travel through large distance. And easily detectable from Earth. So if we, for example, if we were to detect higher energy ETI signal, we would have to send space probe, which would be a more expensive project in that sense. So I think there are a lot of appeal of using radio to detect ETI signals.
Yeah, and also
Okay.
another thing is radio waves are not attenuated by gas and dust in the interstellar medium. So just like, I mean, unlike the optical, we have a higher chance of detection. Yeah.
Okay. So that addresses that. We'll get that one out of the way. I do have another question from the audience, and as always, audience, you are free to send questions to us. They will get passed on to me. So I'm gonna. This one's I like this one too. Are there any of the RF components that are off the shelf, or are they custom purpose built?
Yeah, these are mostly off-the-shelf components, which basically consist of FPGAs and GPUs. The first part of the processing is done by the FPGAs. As I earlier said, these are, you can think of these as computer chips to do some specific purpose. So the first part, where the data collection and the conversion to a particular Ethernet format is done by the FPGAs. And once we do that, for the processing of the data, SETI searches, all those are done in GPUs, which are also known as graphical processing units.
Mm-hmm.
Yeah.
When you talk about the processing the data, what is that looking at? Are we talking, is this a machine learning algorithm? Or is somebody having to go through stuff by hand? Is this almost requiring a SETI at home approach like UC Berkeley did? What are we talking about for processing the data?
Do you want to answer that question, Cherry?
Sure, I'll take a stab. Yeah, this is a really good question. In fact, with the VLA, we are going into a new era of radio astronomy. We'll have commensal observation, will be on sky 24/7, right? So we need to come up with a real-time processing that is able to cope with the data on the fly. We can't afford to save them and then think about what we want to do later, because it keeps coming. So when we talk about data processing, there are multiple stages. First, we need to acquire the data, and then we are going to form these so-called beams. Basically, we are going to create many different line of sight so that we can search for multiple stars to detect potential ETI signals from all of these stars. At the same time, we'll then also need to search for, so it will form these line of sight to point to these different stars. And then for each sky location, we need to check and see if there's drifting signals that might be coming from an ETI transmission. And the main idea here is to do the traditional drift search, but also by incorporating innovative machine learning algorithm to try and detect in real time.
How much, out of curiosity, how much data are we talking about, say, daily or weekly or annually, whatever sort of measurement you have handy? What are we talking about here?
So from the telescopes, we are getting around, we'll get around 3.7 terabytes per second. That's the data right coming from the VLA antennas.
Wow. And so you're talking about running this 24/7 at about 4 terabytes. Okay. Yeah, no, you can't store that someplace.
We need a real-time pipeline. We cannot
you can't just pop that on a server somewhere and say, oh, we'll get to that later, because you're going to fill up a server in what, like 15 minutes? Okay, so what's next? You've installed the amplifiers and the splitters. You can now get the data. So what's happening now with the project?
So at the moment, we are ready to get signals from all the VLA antennas, and we are waiting for a couple of lots of cables actually, which needs to connect between. So the data that comes from VLA antennas are optical signals, and you need some other instrument known as a demultiplexer actually. So you need to convert that, take the data and feed them into these FPGAs and do some other processing. So we were actually testing some of the cables, and we have having some issues, but we have ordered a lot of new set of cables, and in next week we are going to do the main installation. And yeah.
So I have more questions from the audience. I want to give a couple shout outs. We have people watching from Mexico City, Montreal, and apparently the Canis Major Dwarf Galaxy. So, okay, welcome. I'm willing to say these things if you're willing to write them, people. Let's talk about a little bit about the signals that you're looking at. What sort of band are you using on this? Are we looking at the water hole at all? Is there something specific that you're looking in as far as what kind of frequencies you're going for here?
So these are Cosmic is a commensal system, which means we do not get to choose the frequency of observation or where you want to point the telescope. That is chosen by the primary user, the scientist who wants to get the data. So, but the array operates from 74 megahertz to 50 gigahertz. So that's like a wide range of frequencies where we can search for, rather than like a small range of frequency.
And it definitely includes the water hole.
Yeah.
So it's that's another cool thing about the VLA. We are going to expand this electromagnetic window to very low and very high spectrum, where some of these regions have just never been searched for ETI signals. Who knows, there might be something there. But we also will get a chance to look at the water hole, provided the primary observer of the VLA has chosen that band.
Okay. Jill Tarter has stated many times that when it comes to SETI, we have basically looked out at the universe, and if we were to consider it as an ocean, we have basically observed a cup, and we have not found anything in it. How would you apply this analogy to what your search is going to be able to do by piggybacking on the VLA research that's already happening?
Yeah, that's the main purpose that we are conducting this commensal observations. So if we look at many of the SETI searches in the past, most of them are either limited by the number of stars observed or how long they were observed. With this system, and there's a news, we are actually going to do the SETI searches with another VLA survey known as VLA Sky Survey. So it's done in like 3 stages, and already 2 stages are completed, and the 3rd stage will be starting in January 2023. So it's not like a normal survey; it's a fast sky survey. So it would be basically covering the whole northern hemisphere. So with this process, when the cosmic goes online during that time, you'd be able to observe around 40 million stars, uh, which is very, very far greater than any previous SETI searches that have been conducted so far.
Wow. Okay. This is far more impressive than I think even my brain had wrapped itself around. Cherry, I'm sorry, I need to ask something from the audience, simply because I'm not very good at explaining it. But can you explain what the water hole is?
The water hole. Well, it is a region of the electromagnetic spectrum around 1 gigahertz, and this is where we think there is possibly a good chance of detecting ETI signal, and that's why there's so much hype about it, I guess.
Why do we think that's a good spot? I mean, I understand that the word, it's the water, but why? Where is that coming from? Why is this such a good idea?
Yeah, so this is because this is the band. So this 1 gigahertz bands is where the hydrogen line and the hydroxyl line are. And this is also a sort of a quieter region of the spectrum. So there's less contamination.
Okay. Okay. So back to processing the data. This is immense, far more immense than I realized. Is there going to be a citizen science aspect to this, or is this all going to be an internal, very quick pipeline?
At the moment, we have not yet designed a citizen component of it, just because of the high data rate, and with all these raw data coming in, we don't have a downlink from the VLA site that is capable of just sending this stuff out. Now, having said that, the real-time processing will generate a lot of promising candidates, and we are going to save sort of a zoomed-in version of the data that correspond to these signals of interest. And I think, yeah, and I do see a lot of potential there that we could involve the public to help us go through all these signals of interest to see if there are anything worth digging deeper into.
So essentially, if I were to relate it to sort of like the Kepler and TESS data, instead of getting all of the raw data and having to go through it manually, what you guys would be doing would saying, hey, we found really cool stuff. Can other people take a look at it?
Yeah.
Multiple sets of eyes, and tell us if you're seeing something really cool here too, or did our computer just kind of go, oh, I don't know what this is, so I'm going to add it?
Yeah, I think like you said, the computer, we're hoping to deploy the computer to do sort of a first stage filtering, just take out all the useless data that contains nothing, and then we'll just keep the most interesting data and share it with the public.
And when you say nothing versus something, so we're talking, just the general noise of the background, and then something stands out. What is that standing out sort of going? What do we think that's going to look like? What are some possibilities there?
Do you want to take that, Savin?
Yeah, sure. So are you asking in terms of data products, like what stands?
Well, what would your computer see? What would the computer see as sort of, okay, that might be a thing, as opposed to, okay, there's nothing here. I'm not seeing anything interesting. It's just general background noise. What sort of would stand out as like a blip in that we could say, oh, that's something to kind of look at again?
Right. Yeah. So we are basically looking for a very narrow band frequency signal which would drift in frequency and time. That's what we are expecting. But there are recently some of the searchers have been focused on broad frequency signals. with some modulation, which could be from an extraterrestrial civilizations. They could be, doing this modulation and intentionally sending them as beacons. But our primary aim would be to focus on the narrowband frequency signals here.
Okay, so something really small that sort of stands out as that's not general noise from an object. It's something very pinpointed.
Yep.
Yeah, and we'll have to go through some sanity check to make sure that it does not come from Earth, for example. So checking the drift rate of the signal is typically one good way.
Can you explain drift rate for our audience?
Yeah, for sure. So the idea here is that if a signal is generated on Earth, because the telescope is also on Earth, then the transmitter and the receiver, the two side they don't have a relative acceleration with respect to each other. So we'll see the signal stationary in time and frequency sort of. Whereas if the ETI signal is coming from an exoplanet or somewhere, then the host object is likely going to have a relative acceleration with respect to the Earth. So during the course of the observation, we'll see the signal drifting in frequency and time. This is typically the telltale sign that the signal is not from terrestrial origin.
Is there the potential that something you might find could be a new discovery that isn't ETI?
Yeah, I think that is also possible. In the recent years, because of the advancement in technology, astronomers have detected new types of radio transients, for example, fast radio bursts, and also things like pulsars, which we already know from, 50 years ago, but we are finding more and more of them. So while we have this data on hand, we could also try and take a look and see if there are these other radio transients hidden in the data.
That would be kind of amazing to solve the fast radio burst question, wouldn't it? that would be great too. So there's a lot of things that it sounds like this particular data set, which is, of course, as you have said, very massive, could possibly help us with. Is Cherry or Savin, is there anything else about this project you want people to know about that I have missed asking you?
Yeah, the one thing I missed is as Cherry was talking about it. So this project has this uses a technology called multicast Ethernet protocol. So just the way we make an independent copy of all the data streams and we use it for SETI purposes, if there are like different multiple users who want to use this data, they can access the data at the same time. So Cosmic will act as a parallel independent observatory which can accomplish multiple science goals at the same time. Along with SETI searches, you can search for pulsars, FRBs, and also do other interesting science as well.
Yeah, like you both mentioned, I think this is a really groundbreaking capability of Cosmic. The flexibility of it and how we can just make copies of the data and then do different processing in parallel. The SETI Institute, we are very open for collaboration. So if there are people out there who have cool ideas of what we can do with the data in parallel while we search for ETI, we are very interested to hear from you.
Okay, so you guys heard that. They're looking for proposals. I have two more audience questions that I'm going to take because they're really cool and I like them. And then we're going to start to wrap this up. So first question, and I'm pretty sure I know the answer to this, but I'm going to ask you guys. Does the atmosphere interfere with the search at all? Is this I have to wait for good seeing conditions, or is this really a true 24/7? Doesn't really matter. You can watch anytime.
Yeah, we can pretty do it most of the time, unless we are looking at some frequencies which is affected by water vapor. But the telescope itself is located in a desert area, so which has very low humidity, so that wouldn't be an issue, I guess. The other thing is the interference from other radio sources, RFIs, terrestrial interference, basically. That could be an issue, but we know like most of the bands which are usually really affected by these sources. So not a big issue. We can continue observations throughout.
And then one last question. Is there a plan to follow up on candidate signals, say using like the ATA or another observatory like Green Bank or anything like that, where you say, okay, we did all this piggybacking, we've pulled all this data together, we found some interesting stuff, now we want to go back and look at it again. Do you have a plan in place for doing so?
Yeah, that's a great question. I mean, Cosmic nominally is a Commensal piggyback project. So yeah, what do we do when we find something interesting, right? One avenue would be to ask for director's time on the VLA telescope, show them that, hey, we found this cool thing. Can we take a small amount of time on the telescope to follow it up? And then the other thing is, fortunately, the SETI Institute and the Breakthrough Listen team, we have a lot of collaborators and making use of international facilities all around the world. Like you mentioned, the Allen Telescope Array is one facilities that we work with. So the ATA will definitely be able to help follow up some of these interesting candidates. But we also have collaborators or partner projects using the Meerkat telescope in South Africa, Parkes telescope in Australia, and so on and so on. So we can see which telescope is in a favorable position that can see the stars or the exoplanets that we are interested to monitor.
All right. Well, thank you, Cherry and Savin, for this talk. I am very excited about this project. It seems to me every time I talk to a project scientist, a project manager on one of these, I'm more excited than I was when I first read it. So thank you so much for sharing the enthusiasm and the excitement of this. I'm really looking forward to seeing where we go with this. As a reminder to our audience, again, we are a 501c3, and we really do appreciate your donations through your Facebook stars, your YouTube super chats, Twitch bits, Twitch subs. All of those things are fantastic. Thank you so much to everybody who has supported us. Coming up next week, I will be speaking with Dr. Mika McKinnon, who a lot of you are familiar with in our audience. She has recently won a very prestigious award in Canada, and we're going to talk about that and her science outreach. And also coming up in May, we have the Drake Awards, and we are going to be awarding our 2022 to Dr. Shelley Wright. And we will be having a hybrid event in person and online to celebrate. It's sort of our annual celebration of SETI science and the field's pioneers. So we're going to have one of our Science Advisory Council will be there to host. And it is May 12th. So if you check on all of our social media or at our website, seti.org, you can find more information on that and how to attend and how to participate. And again, thank you everybody for watching. Thank you, Cherry. Thank you, Savin, for answering my questions, answering the audience questions. This has been really fun and I've really enjoyed it. So everybody, thank you for joining. Thank you for supporting, and we'll see you next